Okay, we're going to start a scientific session on superfluidity, although I'm not sure all the talks pertain exactly to that. The first speaker is David Merman from Cornell, someone that has worked with Tony known Tony for a long time, and one of my old professors, actually.
I was shown how to turn this on, and I've forgotten already. Where is...
Here, just this thing. There we go.
Good. Can you hear me back there?
What?
Good. Good. As suggested, this is going to be yet another backward-looking talk, with apologies to Tony. There's a forward-looking bit at the end, if I have time to get to it, but it has many dispensable pieces in it. So let's start by looking backwards. The first time I heard the name A.J. Leggett was 51 years ago, when Tony was 29. And I have evidence of this. There was actually a published note added in proof at the end of a paper I wrote in 1967 in Physical Review. I'd found a simple proof that a normal Fermi liquid, there's low temperature physics coming in, had to support what Landau called zero sound. And my proof used a plausible, highly plausible field theoretic conjecture that I couldn't prove. But it was so plausible that I wrote a paper anyway. It was accepted. And I sent preprints to Gordon Boehm and Leo Kadanoff, who were young faculty here in Urbana. One of them evidently showed it to Tony, who was there as a postdoc. Do you remember this? I got a letter from somebody I'd never heard of explaining that the gap in my argument was filled by some analysis he'd published 2 years earlier. So my life with Leggett, which by the way is the title of my talk, began with my viewing him as a brilliant young formalist who was much better than I was at manipulating Green's functions. And for those of you who know Tony well, you will realize that this is a somewhat peculiar way of thinking of him, but that's how he entered my life. I can't remember our specific interactions over the next half dozen years. We must have met several times, because when Tony spent a month at Cornell in 1973, I remember it very vividly as an unexpected visit from an old friend. This was a year after the discovery by Osherov, Richardson, and Lee of strange magnetic phenomena in liquid helium-3. More low temperature physics. The visit was arranged by Bob Richardson, and I couldn't have known Tony all that well because I also vividly remember wondering why Bob was interested in bringing to Ithaca a brilliant young formalist. Tony sat for a month in the office next to mine, and I had the pleasure of watching him day by day make increasingly good sense of those crazy magnetic resonance signals that were coming from the helium. I was actually quite pleased to discover from an acknowledgement in Tony's paper on the work he did at Cornell that I had told him about a strange way of thinking about spin one angular momentum states that I'd learned as a graduate student from Julian Schwinger. I can no longer remember what it was I told him, but I'm pleased that I was not completely passive during his visit. My next specific memory is of a sweltering week with Tony during one of the hottest English summers of the 20th century. This was at something that was called the Sussex Symposium on Superfluid Helium-3 in 1976. And the Sussex Downs, which are normally about as green as grass can get, looked like brown Southern California hills. That visit led to my spending an entire year with him at the University of Sussex 2 years later. I can pin that one down because of two historic disasters, the Iranian Revolution and the ensuing hostage crisis, and the election of Margaret Thatcher as Prime Minister. Actually, speaking of weather, it was one of the coldest English winters of the 20th century while we were there. I lived on a very steep hill. The road was covered with ice, and I watched all my English neighbors sliding and slipping, trying to get up and down the hill. And finally, as a brash American, I took a large bucket of ash from our fireplace and went out and spread it on the street, several buckets actually, down the hill. After that, nobody had any trouble, and nobody complained that I had sullied the roadway. Anyway, Tony came to my lectures on topological theory of defects. I attended his on the foundations of quantum mechanics. Clearly, I did not pay enough attention because I was out of town lecturing when John Bell came and visited Tony and gave a colloquium, and as a result of that, I did not meet Bell until a year before his early death. 1 year later, 1980, Tony visited Cornell. He was one of our earliest beta lecturers. What I remember most about that visit is that he gave a lecture on quantum foundations that finally did catch my attention and persuaded me that there were issues here worth thinking about. But I must promptly have forgot about it again, since it was at least 2 years after that that I finally started thinking about such questions. Now, in 1981, Tony played a dramatic role in the paper that made me famous. This was an essay in Physics Today which described my campaign to make the word boojum an internationally accepted scientific term. When Physical Review Letters agreed to let me use the term boojum, they questioned my use of the plural. I had made the plural boojum booja. I consulted Tony, who insisted that it would have been evident to any ancient Roman that boojum was a word of foreign origin. And he said words of foreign origin are indeclinable. Therefore, if I wanted to Latinate plural, it couldn't be booja. It had to be boojum. 1 boojum, 2 boojum. So we had to compromise, and physical review letters used boojums, and people all over the scientific world are using boojums to this very day. But a few years later, boojum appeared in the Russian literature. The Russian boojum offered spectacular counterexamples to Tony's theory that highly inflected languages would treat the word as indeclinable. In one page, I found the nominative plural, boojumui, the genitive plural, boojumov, and the instrumental singular, boojumom. A few years later, a paper came out that used the instrumental plural, boojumami. I sent Tony, is the mic still working? It is, good. I sent Tony a copy of a paper with specimens of many different inflected boojums. It's very peculiar not to be able to see you out there. Here is Tony's reply to my letter. I bow, however reluctantly, to the wisdom of the majority. I anticipate that we shall now presumably be getting from Accra reports of Maboojum, and from Singapore of Boojum Boojum, while those investigated by Oli Lonisma will presumably behave Boojuksesti. I have an undateable memory of being with Tony in Sicily. We were at one of those meetings in Erice, and I can't remember whether the subject was helium-3 or quantum foundations. There was an excursion, do you remember this, to the Greek temple and theater at St. Justin? I have never before or since heard him speak so loudly, slowly, and clearly. It was an enchanting moment. Ah, yes. Now I have to correct Eduardo Fradkin. The paper entitled, Is the Moon There When Nobody Looks, was my paper. It appeared in Physics Today, and it got 500 citations at latest count. It's okay, because the paper is the flux there when nobody looks. And do you remember, were you really asked to change moon to flux? No, I don't think so. Because you wrote it with Anupam Garg, who was my graduate student during your last visit to Cornell, and who you took back to Urbana with you as a postdoc. And I was honored by the fact that they modeled their title on mine. And I'm happy to tell them that their paper has received 1,000 citations. So it's reasonable that you should have been confused. Oh, good. Some of my most interesting exchanges with Tony have been in referees' reports. As a referee, he was always anonymous, but his written voice was impossible to disguise. In 1993, I sent a manuscript to Reviews of Modern Physics updating John Bell's 1966 critique of von Neumann's 1932 hidden variables theorem. The referee of my paper remarked that the author considered himself to be a writer of fine scientific prose, but, he added, citing one horrible sentence, here was an instance where Homer nodded. I had no idea what that meant. Google being unavailable in 1993, I called the only physicist classicist I knew to ask him about Homer nods. Ah, Tony explained. It means that even the best of us sometimes mess things up. So nod meant not to signify agreement, but to doze off. And I filed this away in my cabinet of useful metaphors. And I fixed the horrible sentence. Last year, I came upon 3 papers by philosophers of science. This is forward-looking, claiming that Bell had misread von Neumann, whose argument actually made perfectly good sense. Swept away in the wreckage of Bell 1966 would be Merman 1993, which I had come to feel was one of my nicest papers. So I got the help of my friend Rüdiger Schack to reread von Neumann, Rüdiger in German, I in English, and we concluded that it was the philosophers, not Bell, who had misread von Neumann, who really had committed a surprising blunder, which was perfectly identified by Bell. Rüdiger and I are working today on a paper to explain this, and thanks to Tony's old referee report, I already know our title. Von Neumann's Surprising Oversight, Homer nodded. Okay, I'm going to skip chapter 9. If I have some time at the end, we can come back to it. One of the great things about the Asherov-Richardson-Lee Nobel Prize was that they were all collaborators, and each of the 3 made full use of his authorization to invite up to 10 guests to the festivities. So in 1996, there was a week-long reunion in Stockholm of many of the wonderful people who had participated 25 years before in the earliest years of the subject. At a time when there was a limited amount of mysterious data to make sense of and a limited number of papers to keep up with. And that is always the best time in any subfield of physics that I've known of. There were more good things to eat and drink than in any week of my life. It was completely exhausting. So, when I heard 7 years later that Tony himself had won the theory version of that prize, I had several reactions. 1, I was impressed that the Nobel Foundation had managed correctly to identify the theorist who had played the most important role in unraveling the mystery of what the hell was going on. 2, my heart went out to Tony for having to repeat at a more advanced age a week that would be even more exhausting than the one we had enjoyed together 7 years earlier. 3, I wondered whether his fellow laureates, Abrikosov and Ginsburg, would give him a hard time for his current interest in as un-Russian a subject as the quantum measurement problem. Now, which brings me to my final chapter. Yes, Tony's views and mine on quantum foundations started to diverge almost as soon as he finally succeeded in convincing me that I really ought to have views. Tony has always been worried by the quantum measurement problem. He's wondered whether quantum mechanics might break down at a certain level of macroscopicity. He's thought about how to design experiments to test for such a breakdown. I, on the other hand, have suspected almost since Tony started me thinking about it, that the quantum measurement problem was not a problem about the world, but a problem about us. That the perception that there was such a problem was a sign that we were not thinking the right way about the nature of our scientific description of the world. My view has the great advantage over Tony's that it's not necessary to persuade anybody to do any experiments. It has the disadvantage that it is necessary to think about how I manage to know what I think I do know. Part of that thinking involves re-examining the nature of probability. Isn't it strange that quantum mechanics, a theory whose meaning people have not agreed on for 90 years, a theory that for the first time builds probability into its very foundations, has not led physicists into a systematic re-examination of the nature of probabilistic assertions. Most physicists still view probability in terms of frequencies and ensembles, a view that many mathematicians and statisticians have rejected in favor of viewing probabilities as numerical measures of the likelihood that personal expectations would be realized. Suppose quantum probabilities are personal judgments about what's going to happen to the physicist who is using quantum mechanics. That raises all kinds of tricky and difficult questions, but it sure does get rid of the quantum measurement problem. A letter to Physics Today once asked how I could possibly believe that wave packets were not collapsing in the early universe, long before there were physicists. My reply was to ask whether the letter writer believed that probabilities were updating in the early universe long before there were statisticians. My own guess, and it's only a guess, is that by the time today's 29-year-old physicist turned 50, when Tony and I turned 101 and 104, everybody will agree that physics is about how we relate to the world. And only historians of science will know what was meant by the quantum measurement problem. I guess that's forward-looking, finally. Physicists might well still think that there is a problem in figuring out just what it is that we are, but I doubt that anybody will call that problem physics. Right on time. Good. Thank you. Happy birthday, Tony.
Okay, thank you. I guess maybe time for one question before, while the next speaker is getting ready. Anybody have a question? Okay, thank you.
No. That's there.
Okay, thank you. Jimmy, you have to put on 2 microphones.
Okay. This one here?
This one's for the closed caption. Okay. You put this in your pocket. Okay, our next speaker is Jim Sauls from Northwestern, going to talk about broken symmetry, superfluidity, I think.
Okay. Let me start by saying to everyone involved here at Urbana that I'm delighted and very honored to participate in this occasion to celebrate Tony Leggett's birthday and to hear reflections on Tony's many achievements and to hear about physics that's grown out of your influence. So my relationship with Tony began without his knowledge by my study of his Reviews of Modern Physics article that was published soon after the discovery of the phases of superfluid helium-3 while I was starting my research as a graduate student at Stony Brook. And that article, soon after its discovery, it was a treasure trove of new ideas on BCS pairing in a system with complex symmetry breaking. And what has arguably become the paradigm for the broad research field of unconventional superconductors. So on this occasion, I want to tell about some new experiments and a few ideas that reveal broken time reversal and mirror symmetry in the first superfluid phase of helium-3 that was discovered and then identified by Tony through his development of the theory of spin dynamics and NMR in superfluid helium-3, what is today still the most powerful spectroscopy of helium-3 in many different contexts. So I expanded my title for this reason because what I want to really focus on is on these new developments, and they center around the broken time reversal and parity of the A phase of helium. So I'll give a little background here, highlight where we're going, and then I'll discuss the new experiments and my interpretation of them. So we'll talk about electron transport in the superfluid phase of helium-3. And so the work that is done is with my collaborators, so Wave Namprutikorn, Alexei Shetsov, and Joshua Wyman. So if you talk to your colleagues in chemistry, they talk about chirality in the context of mirror asymmetric polyatomic molecules, enantiomers such as these amino acids, which have left and right-handed versions of one another. In in quantum condensates, we can have chirality present in a diatomic molecule that forms in, say, a p-wave orbital state, such as this, such as helium-3. You have mirror asymmetric partners due to the motion of the diatomic molecule. So these diatomic molecules break both the mirror reflection symmetry, and they also break time inversion symmetry. And so this ground state's realized in the A phase of helium-3, and possibly other superconductors. So why are they interesting? It's a topic that's been driven a lot by interest from the theory community. These condensates of these chiral molecules lead to an emergent topological property of the ground state, and that's connected with new types of excitations that are of interest in topological quantum matter. I got interested in this subject through a discussion that Tony was instrumental in highlighting already back in the mid-'70s, which was on the fact that a condensate such as this should have a macroscopic ground state angular momentum. And there was many papers written on this subject. Tony, David Merman, and Anupam Garg, and Mike Stone, and many other people addressing this topic. And it's, of course, intimately connected with the broken parity and time reversal of the ground state. And I want to highlight this aspect in a different context, which is anomalous Hall transport of charge in superfluid helium-3. So where are these chiral condensates? The A phase of helium-3, I believe you can say now it is definitively chiral, and based on a strong comparison between theory and experiment. Strontium ruthenate was proposed as the electronic analog of the A phase, and there's evidence from optical experiments of chirality. Uranium platinum-3 is, in other ways, an electronic analog of helium in that it exhibits multiple superconducting phases. And it also shows similar evidence for chirality in polar Kerr rotation at optical frequencies. So to set the context, here's the low temperature phase diagram of the pressure versus temperature of superfluid phases of helium. They were discovered by Pomeranchuk cooling along the melting curve here by Doug Oshroff, Bob Richardson, and Dave Lee. The first signal was seen here at the A point, and the second at the B point. But the identification of these phases as in the liquid and ultimately as a superfluid came from nuclear magnetic resonance measurements shortly thereafter. And these are a representation. These are not the original ones. These are more recent measurements showing the nuclear magnetic resonance frequency shift away from the normal frequency as you cool through the normal state. You see an onset, a continuous onset here. That's the onset of superfluidity. Then there's a first order transition to another state. And that was kind of roughly the picture that Tony saw at the time. And he wrote his famous paper in '72, shortly thereafter, recognizing that frequency shift had the implications that, first of all, it was derived from the nuclear dipolar interaction between the nuclei of the helium-3. And in order to get this shift, you had to have the parent state of the superfluid break spin-orbit rotation symmetry. And then Tony basically worked out the identification of this phase as a state which had spin 1, odd parity, and it was what he called an equal spin pairing state, an equal amplitude for 2 of the 3 spin populations of the spin triplet manifold. So what we now understand is that this was a transition into the equal spin pairing state, which is also now known to be a p-wave state. And this was the first order transition into the B phase. And pretty much the absence of any signature in the spin susceptibility, magnetic susceptibility here, was connected with the fact that this is an equal spin pairing state. Now, there's, as you can see, the A phase is interrupted here by the B phase at lower temperature, but there are a number of ways to stabilize this equal spin pairing state at all temperatures down to the absolute zero. So, in particular, you can confine helium-3 into a film, dimensionally confine it, and you can stabilize it down to zero temperature. Just to set the scale, this is roughly 1 micron, if we multiply here. And the A phase has been now detected by NMR, by the Royal Holloway group, down to 100 nanometer thin cavities. So we have seen the A phase down in this region here. So what I want to focus on is the NMR probes the broken spin orbit rotation symmetry of the A phase. What I want to focus on is the signatures of the breaking of both time reversal and parity in helium-3A. And one of those signatures is the ground state angular momentum, which, at least in the very thin film case, edge state theory tells us that the angular momentum should be basically the number of Cooper pairs in the system times Planck's constant. But this is an open question. There's still no experimental confirmation of this, but there are new experiments being developed at KAIST in Korea by Hyun-Sung Choi's group, micromechanical resonators, torsional oscillators to measure this ground state angular momentum. So maybe we will have an answer to this, this long-standing problem in the near future. So what is the evidence that the A phase is chiral? I will argue that the best evidence, the most direct, is the observation of anomalous Hall effect of electrons moving through the A phase of helium. And this effect is connected with the broken P and T symmetry that I mentioned before, and the topology of the A phase that results from the condensation of these chiral pairs. And the combination of the two, particularly in the thin film limit, leads to the concept that there are chiral edge states, or chiral edge fermions, on the boundary of any particular object that you place into helium-3A. So just to give you the flavor of the topology, this is a map of the Cooper pair, or the order parameter on a Fermi surface. And if we take a traversal around the Fermi surface, this amplitude winds by plus or minus 1, which is just the angular momentum quantum number of the Cooper pairs. That has implications that in 3 dimensions we have gapless fermionic excitations near the nodal points. And in 2 dimensions, if we were to, say, have helium-3 on a cylindrical Fermi surface, or dimensionally confine it, we can have these edge fermions, these massless fermions appear on a boundary. So if we imagine having a sea of 2-dimensional helium-3 here, and we were to poke a hole in it, a small hole of radius r here, it will develop an edge current from these chiral fermions, and that edge current we can compute. The quantized sheet current is 1/4 NH bar, where N is the helium density, and we know that it circulates circulates relative to the chirality of our Cooper pairs. And if we move this hole from one point to the other, the currents move with the hole. And so we can see that the hole actually inherits an angular momentum from the condensate, which is, is basically the number of missing Cooper pairs in the hole times h bar, and it has the opposite chirality of the ground state. So what? Nature gives us a hole, and we can take an electron and push it into the helium, and it will form a self-trapped polaron. It will, the Coulomb interaction of the electron with the electron clouds of the helium atoms combined with the zero-point motion of the electron stabilizes this thing into a little vacuum bubble of a size of about 3 nanometers in diameter. With a large effective mass, roughly 100 helium-3 masses. And if we push it through the liquid with an electric field, it achieves a terminal velocity that determines then the magnitude of its mobility. And one of the facts about helium-3, even in the normal state below about 50 millikelvin, is that that mobility is dominated by many scatterings of the wind of thermal quasiparticles off of this bubble, and the mobility becomes independent of temperature below about 50 millikelvin. Now, if we do this in the chiral phase, we push the electron bubble through the A phase of helium-3, we have a new possibility. And this was pointed out first by Rita Salmalin and Marty Salama and Valery Mineyev. They said the broken mirror symmetry and time reversal symmetry of the A phase allows for an additional term in the mobility, and that term is a Hall response. So we should look for a Hall response where the chiral axis of the Cooper pairs plays the role of the magnetic field. This is just a calculation that Alexei did of the actual structure, the ground state structure of the electron bubble. The electron bubble, we know exactly its dimensions based on the measurement of the normal state mobility. You can calculate the chiral currents here, and they generate an angular momentum of the electron bubble, which is roughly 100 h bar. Now we can imagine taking this electron bubble and pushing it through the wind of thermal Bogoliubov quasiparticles. And so qualitatively what happens is quasiparticles that scatter with impact parameters such that they're co-moving with the chiral edge currents here that circulate the bubble give a different contribution to the transverse force than those moving counter to the edge current, and so we get skew scattering. And that was the motivation for the experiment that was carried out by the group in Riken, headed by Kimitoshi Kono and Hiroki Ikegami, and Susumi-san was a young theorist working together with them. They loaded up a film of helium-3 with electron bubbles. They split a pair of electrodes here. They drove the bubbles downstream with the voltage. And then they split these electrodes to look at the current response on the right and left electrode. And what they were looking for, of course, was to see an asymmetry in the current response generated by skew scattering. And so they did that. And then they were also fortunate. They did many runs. They could get either chirality. And indeed, the sign of these currents switch with the chirality of the ground state. So this is a trace of the, I forgot to say that these were done at low frequency AC. So there's there's 2 quadrigers of the current response. And here they both are. And this is a trace coming from the normal phase of helium-3 directly into the A phase of helium-3, the chiral phase. And you see the onset of the asymmetry in the current response here. say run 1, and likewise in the other quadrature. And another run, it flipped the sign, and so they had the opposite chiral ground state for the other run. If you drop a little magnetic field down to, such that you go from normal phase into A phase, then into B phase, the B phase is time reversal symmetric, you can mark that transition by seeing a slight change in the drag force, the longitudinal mobility. And so it's seen very clearly here. The B phase has a larger gap, so you see an increase in the mobility in the B phase at the same temperature. And now you can see as you sweep through this second trace here, you go first into the A phase. You see exactly the same transverse current response. Then you hit the AB transition line, the asymmetry in the current response disappears, and that indeed is a reversible phenomena. Even the phenomena is reversible. The TAB line, of course, has hysteresis. So I was in Recon when they showed me this data. I was convinced the first time I saw this that they basically had seen the broken mirror symmetry and time reversal symmetry of the A phase. So this is just a summary of the same data before, and then this is the measurements of the Hall angle, or the Hall ratio, showing it onsetting at TC for two different densities of electron, of negative ions. So what's going on? For the average motion of the electron bubble, it's being driven by an electric field, and the response is due to quasi-particle collisions off of the ion. And in the low velocity limit, we can represent that as a Stokes drag tensor. And the broken PT symmetry allows for this off-diagonal Hall term. So if you rewrite this, you see the driving electric field, you see the usual drag on the electron, and then you see a transverse force of the Lorentz form. And if you translate that Hall term into an effective magnetic field, it's about 10 to the 4th Tesla. So it's stunning when you play with these numbers this way. So indeed, that's what comes out. You can translate, of course, the Stokes tensor into the mobility, which is the quantity the Recon group reports. So Alexei and I wanted to make a theory of this, and it's a scattering theory, and it's in much the same spirit that Gordon Boehm and Chris Pethick developed for the B phase of helium some time ago. We start by formulating the scattering of Bogoliubov quasiparticles off of the ion, and we want a low energy theory that describes the superfluid phase. So all of the high energy physics is subsumed into the normal state T matrix here, and then we have the propagator for our Bogoliubov quasiparticles, and the new key piece of this equation here is the off-diagonal pair potential here. And since it's chiral, this quantity here induces branch conversion scattering of particles to holes or vice versa. And by that I mean you can start with a quasi-particle excitation here in the superfluid phase, and it can exit in the final state as a quasi-hole or vice versa. And the fact that this is a chiral state means that exiting, that branch conversion processes transfers 1 unit of angular momentum. And that is the origin of the transverse force. So it's this combination of potential scattering and branch conversion scattering that I believe is the root of the skew scattering that occurs in helium-3A. So the only other piece of information that we need to parameterize the T matrix for normal state quasi-particles scattering off the ion. And that turns out to be very well described by a hard sphere potential. And we actually know the radius precisely from the normal state mobility. So this is what the differential cross-section for a Bogoliubov quasiparticle ion scattering looks like for an electron bubble at basically the lowest pressures. It's 11.17 Fermi wavelengths is the size of the ion. Quasiparticle comes in, scatters off of this ion sitting at the origin here, and you see a massive reduction in the backscattering. This is something that Gordon Boehm and Chris Pethick discovered in the context of the B phase, as you get a substantial reduction in backscattering and enhanced forward scattering. But what you see in the case of the chiral quasiparticle scattering off the ion is you see these 11 resonances here. And these are resonant scattering reflecting the underlying bound state structure of these chiral edge states that are bound to the ion. And you can read them off here. And then you see the asymmetry in the differential cross-section, which gives you the net force on the ion in the downward direction here. So if you put this cross-section together with the kinetics to compute the total force acting on the ion, you can compute the drag forces once you know the hard sphere radius. And this is the comparison between the theory and the experiment over a little over 2 decades in mobility. And this is the Hall ratio, showing the onset at TC, reaching a maximum, and then unfortunately the data stops about 230 microkelvin. So that's where in spite of the fact that we're very satisfied with this theory has to fail. And it has to fail further dramatically at low temperature as this mobility climbs. And there are a number of ways to see how that takes place. And I'll highlight a couple of open problems, one of which is what happens at very low temperature. And I believe also this theory provides some motivation for looking for a bulk signature of broken time reversal symmetry in chiral superconductors using the thermal Hall effect. But let me just highlight what goes bad with this theory. If we look at the effective magnetic field that comes out of the scattering theory, at low temperatures it decreases as t to the power 4. So that would, if you took it seriously, you would take an electron bubble, give it a little tiny impulse, and it would move in a straight line, in spite of the fact that it has this angular momentum of 100 h-bar moving through a chiral vacuum. But another signature of what's breaking down is if we look at the Reynolds number for a moving object of a radius r through this fluid, the Reynolds number moves from a laminar-dominated regime or viscous-dominated regime to a force-dominated regime at about 100 microkelvin. So certainly I think this theory is going to break down just from a hydrodynamic point of view. Probably more serious is the fact that the critical velocity, there's actually no abrupt critical velocity in the A phase due to the fact that it has nodal excitations. So there's a slow crossover in which the motion of the ion as you go to lower temperature and the drag decreases, it blows up, and this whole theory of scattering has to break down, and we have to cross over to a radiation-dominated regime. So that, to me, is, at least in my mind, is the unanswered question: is how does this happen? In fact, we have a transverse component of the radiation back action as we push an electron bubble at 0 temperature through a chiral vacuum? I suspect we do. But it requires a theory, I believe, that's more detailed and includes the stochastic dynamics that takes place as an electron bubble accelerates in the electric field, emits excitations, decelerates, and we have to keep track of these many stochastic processes. So with that, Tony, I just want to say happy birthday, and thanks for all the beautiful physics and all the things you've stimulated over the years.
Are there any questions?
What are the blue lines in the last view?
Yes. I imagine they're particle hole pairs. They're excitations of quasi-particles out of the vacuum.
Can you repeat the question?
Yeah.
Can you repeat Tony's question?
Yes. What were the blue lines in this last figure, right? Yeah, so I have an electric field in this direction driving my electron bubble. This is some sketch of a possible trajectory, average trajectory of the electron bubble. If you imagined it starting off accelerating the bubble at 0 temperature, there's no thermal excitations to slow it down. It will accelerate up. I think it will emit randomly a pair of excitations or excitation out of the vacuum, decelerate, and accelerate again. That process will be random, and so you'll get a stochastic motion of the electron bubble emitting a radiation out of the vacuum as it gets accelerated by the field. And the question is that radiation process also chiral? Will it produce a net back action that gives you a transverse force? I believe it will, because the bound state spectrum around the ion, which gives rise to the scattering resonances, is also chiral. But it's unknown. And we're trying to formulate this as a type of Feynman-Vernon theory for the motion of the mesoscopic ion in this chiral bath. So.
Okay, thank you. Okay. Is this your? This is yours here.
You can use mine if you wish.
It's just a laser pointer, or it's also...
It is a laser pointer. It'll also do your slide transitions.
I'll just use it as a laser pointer. I'll get too confused. So.
Yeah. I just worry that the batteries will go on you.
Here is the.
So what is this? Oh, this is the microphone?
No, we have two. I'll explain. We need both of them.
You need them both?
One of them is closed caption.
Okay.
Or a bit of a deaf student right there.
I have to put it in the same place, more or less?
It seems to work.
Okay. And that goes in my pocket.
Yeah.
Put this in here, Jim. You're going to use it.
Am I on?
What's the problem? Oh, okay.
I pushed HDMI.
Yeah.
Oh, you got to turn them on again. Okay. But,
You want to do a full screen. And this thing is working, I guess.
yeah.
Okay, our next speaker is Jim Eisenstein from Caltech. He's going to speak on an almost superfluid.
All right, well, it's truly an honor to be here to give a talk at Tony's 80th birthday. I really appreciate it. Unlike many of the people in the audience, I haven't had the benefit over the years of really having a close collaboration with Tony. We've served on various committees over the years, but I haven't really been able to spend much time talking science. I do remember, though, in my own career, two little vignettes that might be interesting. One was, like Jim was mentioning, I was a graduate student in the 70s working on Helium-3, and I remember reading Tony's Review of Modern Physics article, and I felt at the time that this was the most amazing article that I had ever seen, and would I ever be able to write something of comparable quality? Well, 40 years have gone by, and I now know the answer, and you can probably guess what it is. The second vignette that I remember, the second instance that I remember, was about the same time. The first conference that I ever went to, my advisor was kind of cheap. The first conference that I ever went to was the 1980 Cornell conference on helium-3. And I was just, wet about the ears, graduate student at the time, just finishing my graduate career. And I nervously went up to Tony and asked him a question. And he answered. It was an amazing experience for me that someone so distinguished would deign to talk to me. I'm so grateful for that experience. Okay, so the work I'm about to talk about is the result of a long-term collaboration with many people who are listed here. It started about 20, 25 years ago at Bell Labs, and it continues in my lab today and elsewhere around the world. So, sort of in a nutshell, if I can get this thing to advance, in a nutshell, here's what I'm going to talk about. So imagine that you have some material, some mystery material that someone's handed to you, and you go ahead and you try to make electrical measurements on it, and the first thing you have to do is make some contacts to it. You put on these contacts and you get out your ohm meter and you try to do an experiment. And you find out that no matter where you put the wires on the sample, it doesn't conduct any electricity. It's just an insulator. However, some young graduate student in the group inadvertently connects 2 more wires and short circuits the device with 2 of the remaining contacts. And lo and behold, current starts to flow, lots of current. And the question in this talk is, why is this happening and how can it happen? And what I'm going to try to convince you is that this happens, at least in the case that I'm going to describe, by the creation of excitons, which are mobile in this otherwise electrically insulating material. And that these excitons can move across the bulk of the material, recombine in such a way as to drive current through the external circuit. And I'm going to hopefully going to convince you that we can demonstrate exactly that phenomenon. So where do you get this? One way, maybe there are other ways, is to start with a double layer 2-dimensional electron gas. And you can forget about how you create such a thing. I'll tell you a couple words about that in a little while. But just imagine that you have this. And make sure that you bring the layers close together. Close meaning the distance between the layers kind of comparable to the distance between the electrons themselves, so that the interactions between electrons in one layer are about as strong as the interactions between electrons in opposite layers. So you have to do that. And in our case, you have to put on a strong magnetic field. Maybe someday we can do this without the magnetic field, but what I'm going to talk to you about today is with a large magnetic field applied. And if you do all these things, and you have the right materials, and you set this thing up this way, you will find that you can construct a condensate of excitons. And that's the system that I'm going to talk to you about. So the various materials that are known to support this particular state of matter, electronic state of matter, the historical one, it's still the one that I use, is a sandwich of various semiconductor layers grown by molecular beam epitaxy, in which the electrons occupy those 2 green, you can think of this as a ham sandwich if you like, and the electrons are in the lettuce, separated by some barrier layer that's quite thin. We can grow these things and make them with whatever electron density you want over some range, and we can tune the distances and the height of the barrier. All these parameters can be adjusted. It's a very nice system. It's very expensive, because molecular beam epitaxy is very expensive. Alternatively, today, you can go out and get Scotch tape and a bunch of dirty carbon, and you can make it this way. And it seems as though it's a good time for me to retire, because now all the physics that I'm about to describe to you appears to be showing up in these ridiculous materials made out of carbon and Scotch tape. That's the way it goes. So those are the 2 systems that I know about so far in which this particular physics that I'm going to talk about has actually been seen. Us old semiconductor guys still have an edge, but it's going away fast. So what's the first signature that you see? So this is a picture of the quantum Hall effect. It's a quantum Hall effect in this double layer structure. Quantum Hall effect is an electrical measurement where you put current through and you measure voltage transverse to the direction of the current, and you discover plateaus in the Hall resistance at multiples of h over e squared. And if you do this in 1970 or 1979, you win the Nobel Prize. But this is an example from the double layer system, and you can see there are various plateaus in there, not very many, but there's one right there, which happens at h over e squared, almost exactly. But there are 2 layers there in parallel with one another. So in a sense, it's occurring with each of the layers you might think of as having twice that resistance. At least if the layers were independent and you've got the current going through both layers, you might imagine that it would be half the current would go in each layer. But each layer in this particular setup has been arranged via the magnetic field to occupy 1/2 of the lowest orbital Landau level that exists coming from the magnetic field. And you also know that if you're a quantum Hall effect aficionado, that if you have a single layer of electrons with the magnetic field adjusted so that the filling factor is 1/2, there is no quantum Hall effect. It's never been seen. But with this double layer system, apparently if you have two such layers and they're close together, there is one. That's the state. Well, that's the first signature of the state that I'm about to talk about. And we got very excited about this. This was a nice thing to see. We didn't realize what really was hiding underneath. So there's various ways to understand this. I'm not going to get into the theory of this at all, but I will sort of point out some of the salient ideas. So if you imagine that these two colored balls, the red ones and the blue ones, are occupying different layers, and the magnetic field is adjusted so there's just as many empty states, because it's half filling, as there are filled states in the lowest Landau level. And if you then orient the system or arrange the system so that electrons in one layer sit opposite to holes in another layer, you might imagine that that could be a specially stable configuration. And in fact, that's the case. And when this kind of arrangement occurs, you in fact expect, from theoretical grounds, that the system will generate an energy gap and create a quantized Hall effect. So you can say, yeah, great, we've discovered this. You also know that there's some kind of one-dimensional, for simplicity today, I'll keep it to one dimension, one-dimensional phase diagram where the variable on the phase diagram is the separation between the layers, and if the layer separation is large, this physics doesn't occur. Electrons in one layer just don't care about what's going on in the other layer, and if the layers are close together, they care a lot, and they form this state, and there's some kind of phase transition in between. That's not good enough. I mean, that's very interesting. The quantum Hall effect is obviously an interesting phenomenon, but it's not interesting enough. And let me try to say what the difference is. So in this case, unlike ordinary quantized Hall states, let's say filling factor 1/3, the fractional quantum Hall effect, there's an energy gap, and there are quasi-electrons and quasi-holes above and below the energy gap. In this particular state, there's something else. There's certainly an energy gap to charged excitations, but there's also a condensate. This condensate was not, I mean, it was known, but it wasn't appreciated really in the early days of this kind of study of this kind of physics. Now, the picture is very similar to this one, where you can imagine a semiconductor has an energy gap, and there are quasi-particles above and below, and a superconductor has an energy gap, but something much more exotic, it has a condensate. This system that I'm talking about today has a condensate too, but the condensate is not Cooper pairs, it's excitons. And excitons are neutral. So whether it has important consequences for experiment is not immediately obvious. You can think about this exciton condensate in the following kind of simplified language, and it's good enough for me anyway, that I have these two layers that are each of them in their half-filled state, and if I choose to make a particle-hole transformation, I can imagine one of the layers being half-filled with electrons, but the other layer half-filled with holes, and then I've got a fully filled Landau level, which I can pretty much ignore, and those electrons and holes attract one another, and you form some kind of ground state. That's another way of describing the physics that was in that wave function that I showed you a couple minutes ago. And indeed, you can convert that wave function into this wave function, which most of you will be very familiar with. This looks just like the BCS wave function for a superconductor, with some differences that are important, but I'm not going to talk about today. So this system has what we call spontaneous interlayer phase coherence. Electrons in one layer actually lose their memory as to what layer they are actually in. This wave function has a phase in it that we believe is macroscopic, at least in the ideal limit of a very, very clean sample. All electrons would have that same phase. We could imagine that if there were gradients in that phase, in analogy to superconductivity, we would have supercurrents of excitons. They're neutral, so maybe they're not any good for anything, but maybe we could find a way to detect them. And I'm going to describe experiments, just one, that shows that you can detect them. Something which was not envisioned in the early days even in the early days of discussions of exciton condensation. Most people thought, these things are neutral, it's just an insulator. But we have experimental techniques that allow us to control what's going on in the individual layers separately. It's a little as though you could grab a hold of the exciton by one end and grab a hold of the exciton by the other end, the positive and the negative, and do different things to them. And if you can do that, suddenly you can control their motion and see what they do. Two experiments that are very interesting in that regard are tunneling, driving an electron from one layer to another. That connects to this condensate, or driving oppositely directed electrical currents through the individual layers. If you try to drive the currents in the same direction, like in that quantum Hall effect experiment that I described, you can't do that using the excitons. They're neutral. You can't transport charge with them. But if you drive the currents in opposite directions, then you're not transporting any net charge from left to right, and you can, in principle, do that by moving excitons along. Okay. The tunneling experiments were really the most dramatic ones that we did at the sort of around year 2000 or so that illustrated that there was something very special about this particular quantized Hall state. And I'm not going to describe much about these tunneling experiments except to show you this one graph. So these are two, the same sample actually. We can control the effective separation between the layers by controlling the density of the electrons. I can start with the system in this blue situation where the layers are effectively too far apart, and the tunneling spectrum is this little blue trace. This is this is actually tunneling conductance. And you can see around zero energy, there's very little conductance. It's very hard to tunnel. This is something we knew about from quite a number of years, and we sort of understood in terms of signal layer physics. But then when we reduced the density such that we crossed that critical point, the tunneling went nuts, right at zero bias. We saw a gigantic peak. And in fact, this is very old data. If you saw newer data, you would find that that peak is extraordinarily narrow. Not zero, though. It's very, very narrow, sort of sub-microvolts. So that told us something fancy was happening. Here's another experiment. It's even easier to understand. So this is a measurement of the Hall effect, the transverse voltage in response to a current. And in the blue situation, again, the sample is set up in such a way that the layers are effectively too far apart, and the Hall resistance goes up. It shows some nice plateaus. But around the magic point, the magic magnetic field, it doesn't do much of anything. There's no quantum Hall effect. Now, in this experiment, I'm driving the currents in opposite directions in the two layers. So this is not a conventional Hall effect experiment. But I am measuring the voltage in one of the two layers. And in the blue trace, it doesn't care that the current is going back the other way in the other layer. It's too far apart to matter. But if the layers are close together, clearly it matters. The Hall effect goes to zero. So this was to me, it was an amazing observation that the Hall effect, due to the fact that I've got the currents flowing in opposite direction, was going to zero. How do you understand that? Well, you have a cartoon picture of it. This is the cartoon. Is that by driving the currents in opposite directions, you're in fact coupling to these excitons. And they are flowing from left to right or right to left, depending on how you want to do your particle hole transformation. And you're getting no voltage from that because these objects are neutral. Well, that's a nice kind of, quote, explanation. And that's the one that we used. However, and this is what the sort of newish thing that I want to talk about today, and will lead to some, I think, further questions. Quantum Hall states are topological. They have, as Jim talked about, I didn't know about this business in helium-3. This is fascinating, that there are edge states in quantum Hall systems. That's their very nature. These edge states are conducting. They run around the perimeter. You can't get rid of them. And they're clearly involved in this transport experiment where the currents are going in opposite directions in the two layers. So what effect do they have? Hard to say. And in particular, and this is the crucial point, because the transport in the edge states is confined to the edge, sort of by definition, you don't really have any idea what's going on in the bulk from this experiment. So what I showed you before about the Hall effect vanishing was consistent with this idea that the excitons were carrying all this counterflowing current, but it doesn't really tell you that this stuff is going on through the bulk. And I've tried to put it to you at the very beginning of the talk that you could get these objects to move through the bulk of an otherwise insulating material. So how do you investigate this question? Here's how you do it. You have two edges. You make your device have an inner ring, an inner boundary, and an outer boundary. Now you have edge states at both of those boundaries, but the two boundaries don't talk because the bulk is a wasteland for charge. You can't get across with charge. We know this since many years. Here's the conductance measured in an ordinary quantum Hall device, measured between these two rims. They've got these edge currents going around, but you can't conduct between the two black dots. So as a function of magnetic field, when you get to a quantum Hall state, the conductivity just vanishes. It gets very, very small. Here it is in an integer quantum Hall state. Here's a fractional quantum Hall state. So we know the bulk is insulating, as I told you before at the beginning of the talk. I want to do that same thing using a double layer system. So for the purposes of not having to draw all these complicated pictures, I'm going to draw these pictures down below in the box to indicate that the contacts, the black dots on the left, are on one boundary, and the contacts on the right are on the inner boundary. And that there's no way for charge, ideally at zero temperature and so on, to get from left to right. And we can make this device, and we can connect these wires, we can connect wires to these contacts in any way that you would like. So the first experiment to do is to connect them like this, in parallel. Well, this is the plain old standard measurement. Put the currents in the same direction through the two layers. Right? That was the original data that I showed you with the Hall plateaus. We were doing exactly that. Here we are doing it again, but in this more complicated Corbino device. And you find, yeah, you get all these things and nice big zeros. And in fact, there, in this particular sample at almost 2 Tesla, the conductivity again vanishes or gets very, very small. And this is the situation where the two layers are individually at half filling, and this supposed excitonic state is occurring. So this is a demonstration that the bulk is insulating in the situation of interest. All right, so now let's do the measurement differently. Reconnect the wires and try to drive current from one layer to the other. That's a different measurement, and that couples to the condensate. Now, truth be told, this picture shows you very little current flows. Here's this current versus voltage. There's very little current. And then I got done, remember earlier I told you the tunneling response was really strong, and where is that? Why isn't that there? And we had to get rid of it on purpose. For the purposes of this particular experiment, we wanted to suppress that tunneling. Okay, you'll see why in a second. And we can suppress it, for interesting physics reasons, by putting a big magnetic field on parallel to the two-dimensional electron gases, in addition to the big magnetic field that's already on perpendicular. We could talk at lunch if you're interested in why that works and what's going on there, but you can kill that big peak. So we killed it. This is very important, because now we did another experiment. The blue trace is the one I just showed you. The red trace is exactly what I showed you in that cartoon at the beginning of the talk. I put a short circuit on the other side of the device, meaning the other boundary, across that insulating wasteland. And now current is flowing. All kinds of current is flowing. So this, if you're still not too hungry for lunch, this should shock you. This is an amazing observation, in my opinion. Here's the summary. There's 2 experiments. No current flows in experiment number 1. Lots of current flows in experiment number 2. How do you reconcile these things? Well, the first thing to do before you start making fancy theories about it is you need to find out where that current is going. And we found, by doing direct measurements of what was occurring in that short circuit, that all of the current we injected on the other rim was somehow managing to get across the wasteland and go through the short circuit. And in fact, this shows a comparison of the current that we were driving, if you like, and the current that we were measuring over here. So all of it was getting across there. The reason this was important was to prove that by some hook or crook, the electrons weren't deciding to find a way out of our suppression of tunneling and jumping across somewhere in the middle. That was important for us to show that that was the case. If we had not suppressed the tunneling, this red current would have been nearly zero. All of the current would have shunted right there right where it came in. So we had to get rid of that. It was essential. So how do you understand this? You can sort of imagine these experiments done in the following way. We have a double layer system, and it's inhomogeneous in the sense that on the right, we've arranged the densities, let's not ask how, to be in this particular excitonic phase, but over on the left, the densities are higher, and you're on the other side, the bad side of the critical point, and so the system, the layers are acting independently. Over there, we can drive currents in the individual layers at will, but on the right-hand side, we have the chance of coupling into this exciton process. And that's exactly what goes on. Electron comes in, bang, it Andreev reflects off of the boundary, if you like, between the two regions. It's not quite Andreev reflection because it reflects as an electron, but in the opposite layer. So no net current actually goes from left to right in this experiment, in this cartoon. So these excitons allow you to transport energy without transporting charge in this electronic system. We can deliver heat to that load by putting a voltage on the opposite side, on the opposite boundary of this topological insulator. Question might be, too many animations, sorry. Does V equal IR? It does in freshman physics. Does it do it here? You might have thought, back a while ago when I showed you how much current was flowing, you might have said, well, why wasn't it 10 times that amount of current? Or 10 times less? What determined the slope of that line? Is it just that external resistor? Or is there some dissipation process going on in the exciton transport itself? Maybe it's not a superfluid, maybe it's got a lot of dissipation. So that's what we want to try to find out. That's actually hard to do in this particular geometry. It's not a very good geometry for trying to do this. But I will say, because I'm almost done here, that to the best of our ability in this Corbino geometry, all of that limitation of the current was coming from extraneous resistances in this circuit, none of which I'm showing you in this picture. You can't get into a quantum Hall system without paying the quantum Hall resistance. That's number one. You have these low-density two-dimensional electron gases that have high series resistances. You have contacts, blah, 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 a long list of things. And those things, to the best of our ability, and these were really indirect estimates, were that they were the entire limit to the current that was flowing. So exciton dissipation is weak, but we don't really know how weak. It turns out that you can do a somewhat better job on estimating how much dissipation there is in what we call the counterflow channel by going back to the simply connected geometries, the Hall bars that I described at the beginning, the ones that don't have a hole in the middle. And you can argue about whether this is a legitimate way to do this. But if you make those counterflowing measurements in the Hall bar, you can measure the Hall resistance. You find out that it's pretty close to zero, like I showed you. You can measure the longitudinal resistance. It's pretty close to zero. And then you can take those resistivities and compute a conductivity. It's a little difficult because it's a 0 over 0 problem, but if you try to do your best, you'll find out that the conductivity in the counterflow channel as a function of temperature appears to go up and up and up as the temperature goes down. But it's not infinite. It just goes up, more or less in a kind of thermally activated way, inverse thermal activation like this. It gets so high, normally in a magnetic field, conductivity of two-dimensional electron gases is vastly smaller than it is at zero magnetic field. But here, the counterflow conductivity actually exceeds the conductivity at zero magnetic field. Meanwhile, if you do the experiment in the conventional way, the conductivity vanishes in a thermally activated fashion. So this is the end of my talk. These are the conclusions that from this particular survey of this problem. We believe that this exciton condensate is there. We've demonstrated, and I hope I've convinced you that the bulk of these systems is in fact opaque to charge, but it's transparent to the flow of excitons. It's a very interesting thing. Exciton transport does appear to be weakly dissipative, which raises some of the questions listed below, in particular the first one. What is this dissipation? Why is it there, and how does it come about? And can we control it, et cetera? And there's various other questions which are food for the future, and I'm confident that they will all be answered in time for your 90th birthday. So happy birthday, Tony. Yeah, no, never tried to do that. We never tried to work in that, it's going to be high frequencies and have not tried that. It's a good idea. Tony has a question.
Is there any analog to the Meisner effect?
Can you repeat the question?
The question is there an analog to the Meisner effect? And the answer to that is, I don't know, but there were a number of predictions that turned out to be false, I believe, when this phase was originally theoretically considered in the 90s, that there would be a Meisner effect. How that would manifest itself, I'm not sure. Subsequent theoretical papers suggested that that was false. So that's the best I can do, I'm afraid, to try to answer that question. Lunchtime.